A predictive model can be accurate, technically impressive, and completely useless in production. It can generate the right number and still fail because nobody knows when to run it, where to store the result, who acts on it, or what happens when it is wrong. The model is not the application. The production system around the model is what creates business value. A predictive prototype can be surprisingly simple. Take some historical data, prepare it, run it through a model, generate a prediction. That may be enough to answer an important early question. Does this idea have potential? But that is not the same thing as having a production application. A real system usually looks more like this: data, preparation, features, model, prediction, business rules, decision, workflow, monitoring, feedback. Each step exists for a reason. The data may come from SQL Server, Azure SQL, an ERP system, a CRM platform, telemetry, files, or external services. Before the model sees it, the application may need to validate values, deal with missing records, normalize units, combine sources, or reject bad input. Then the model produces a prediction. But that prediction usually does not directly become a business action. Suppose the model predicts a 78% probability that a machine will fail within 10 days. Does that automatically shut down the machine? Probably not. The application may apply business rules. Is the machine critical? Is maintenance already scheduled? Are replacement parts available? What is the production schedule? What does the operations manager want to do? Now the prediction has become part of a decision process. Production also requires failure handling. What happens if the source data is missing? What happens if a service is unavailable? What happens if the model produces an impossible value? What happens if today's prediction is dramatically different from yesterday's? What happens if the system stops generating predictions entirely? A demo can ignore many of those questions. Production cannot. This is the architecture distinction I want enterprise teams to remember. A prototype proves the predictive capability. A production application operationalizes it. The model generates the prediction. The application makes the prediction usable, governable, supportable, and actionable. That is where most of the real engineering work begins. Predictive AI does not require an organization to abandon the technology stack it already knows how to build, secure, deploy, and support. For a Microsoft-centric enterprise, the predictive capability can often fit naturally inside an existing .NET architecture. C# can handle the surrounding application logic. .NET can host web applications, APIs, background services, integration processes, scheduled jobs, and business workflows. SQL Server or Azure SQL may already contain the operational and historical data. ML.NET can support a range of machine learning scenarios directly inside the .NET ecosystem. And when the best model comes from somewhere else, ONNX can provide another useful option. A model may be trained using another framework, exported to ONNX, and then executed inside a .NET application. Azure Machine Learning or other Azure AI services may also make sense when the organization needs managed training infrastructure, experiment tracking, model registries, scalable endpoints, or centralized machine learning operations. The architecture should be driven by the requirement, not by ideology. If an internal forecasting job runs once every night and processes 50,000 records, a scheduled .NET worker may be completely adequate. If the organization needs centrally managed models serving multiple applications at large scale, an Azure-hosted endpoint may be more appropriate. If the predictive capability belongs directly inside an existing line of business application, embedding it into that application may produce a simpler operational model. One assumption I regularly push back on is that machine learning automatically means Python. Python has an enormous machine learning ecosystem and may absolutely be the right tool for some work. But that does not mean the production business application has to become a Python application. The organization may already have .NET developers, existing C# applications, Microsoft Identity, SQL Server, DevOps pipelines, logging standards, security controls, deployment standards, support teams. Throwing all of that away because the project contains a predictive model is not automatically modernization. Sometimes it is simply architectural churn. Use the best modeling technology for the problem and integrate it into the enterprise architecture that makes operational sense. For many Microsoft organizations, .NET can remain the application backbone around the predictive capability. Users usually do not want another AI system to log into. They want their existing business systems to make better decisions. That distinction should influence the architecture. Consider an ERP application. The purchasing team is already reviewing inventory levels, open orders, supplier lead times, and purchase recommendations. If predictive AI can estimate future demand, the most useful architecture may be ERP, Forecasting API, Predicted Demand. Then the prediction appears inside the purchasing workflow the team already uses. Now consider maintenance. The maintenance application already contains equipment, work orders, inspection history, parts, technicians, and schedules. A failure risk model can become one more capability inside that system. The user does not need to care whether the score came from ML.NET, an Azure endpoint, an ONNX model, or another service. The user needs to know, this machine has elevated risk. Here is why it matters. Here is what I can do. The same pattern applies to CRM. A churn model produces a probability. The CRM application turns that probability into something useful. A prioritized account list, a task, an alert, a recommended review. Scheduling systems can use predicted workload. Financial systems can use payment risk scores. Operations dashboards can use demand forecasts. Custom .NET applications can call a prediction component just as they call any other business service. Architecturally, this means prediction becomes a capability. It does not have to become the center of the system. A common mistake is building an impressive standalone AI platform with its own dashboards, users, workflows, and security model when the actual business process already exists somewhere else. Now the organization has duplicated work. Users must switch systems. Data has to be synchronized. Permissions have to be maintained twice. And somebody must decide which system is authoritative. A better question is, where does the decision already happen? Then ask, how can prediction improve that decision? Put the predictive capability as close as practical to the workflow where people already act. That usually improves adoption, reduces integration friction, and keeps AI connected to the business process it is supposed to improve. One of the easiest ways to over-engineer predictive AI is to assume that faster is always better. It is not. The correct prediction frequency depends on the business decision. Suppose a company forecasts monthly demand. Does that prediction need to be recalculated every second? Probably not. Nightly may be more than enough. In some environments, weekly may be sufficient. A background service could collect the required data, calculate features, run the model, store the results, and finish before employees arrive the next morning. That is batch prediction, and batch processing has real advantages. It is usually simpler to schedule, simpler to monitor, simpler to retry, simpler to audit, and often cheaper to operate. Other situations genuinely need faster predictions. Fraud scoring may need to occur during the transaction. A recommendation may need to be calculated when the user opens a screen. A machine telemetry system may need to evaluate incoming measurements continuously. A customer risk score might be refreshed whenever an important event occurs. Those are on-demand, event-driven, real-time, or streaming patterns. But each step toward real-time adds architectural consequences. More infrastructure, more concurrency, more availability requirements, more monitoring, more retry logic, more failure scenarios, potentially more cost. If a purchasing manager checks inventory forecasts once every morning, building a streaming architecture that recalculates demand every 5 seconds may provide no measurable business advantage. You have created complexity without creating value. And that complexity follows the system into testing, security, deployment, support, disaster recovery, and troubleshooting. This is where the business requirement needs to drive the engineering decision. Ask, how frequently does the underlying data change? How quickly can anyone act? How much does prediction freshness affect the outcome? What is the cost of being 1 hour behind, 1 day behind, 1 week behind? My default rule is simple. Use the slowest prediction frequency that still supports the business decision. If nightly works, nightly is good architecture. If real-time creates measurable value, build real-time. Production engineering should solve the actual timing problem, not the most technically interesting version of it. A predictive system can fail without crashing. That makes it different from many traditional application failures. The API may still return HTTP 200. The database may still be online. The scheduled job may complete. The screen may still display a prediction. And the model may quietly be getting worse. One cause is data drift. The incoming data changes compared with the data used during training. Perhaps customer behavior changes, product mix changes, prices change, a sensor is replaced, a source system changes how a field is populated. Another problem is concept drift. The relationship between inputs and outcomes changes. The same signals that predicted customer churn 2 years ago may no longer work as well today. Model degradation is therefore not always a software defect. The world around the model may have changed. That means monitoring needs to go beyond uptime. The organization should log predictions, log important input characteristics, record the model version, record when the prediction occurred and when the real outcome eventually becomes available. Connect the outcome back to the original prediction. Now we can compare predicted versus actual. That creates the basis for measuring error over time. Missing data also needs attention. Suppose a forecast normally uses 12 features and one important source suddenly stops updating. The model may still return a number, but should anyone trust it? A production application should be able to detect that situation, log it, alert when appropriate, and potentially suppress or qualify the prediction. Versioning matters as well. If model version 12 produces a prediction today and model version 13 replaces it tomorrow, the organization should know which model generated which result. Otherwise, troubleshooting becomes guesswork. Retraining should also be deliberate. Retraining every night is not automatically better. Retraining once every 3 years is not automatically worse. The correct schedule depends on how quickly the underlying patterns change and whether performance is degrading. The operating loop should look something like this: predict, log, observe the actual outcome, compare, detect degradation, investigate, retrain or replace when justified. Production predictive AI needs observability of prediction quality, not just application availability. If nobody is watching whether the model is still right enough to be useful, the organization does not really have a controlled production system. It has a model running unattended. Predictive AI does not have to make the final decision to create value. In many enterprise applications, the safer and more useful architecture is the model recommends, the person decides. Suppose the system predicts an inventory shortage 2 weeks from now. The application does not automatically place a $50,000 purchase order. It puts the item into a review queue. The purchasing manager can see the forecast, current inventory, open purchase orders, supplier lead times, and perhaps a confidence range. Then the manager decides. Consider customer churn. A model identifies 20 accounts with elevated risk. That does not mean the system sends an automated discount to every customer. It may tell an experienced account manager, these accounts deserve attention. Now the employee can review relationship history, contracts, open issues, customer sentiment, and other contexts that may not exist in the model. Predictive maintenance works the same way. High failure probability may trigger an inspection. The maintenance manager can combine the prediction with operating schedules, parts availability, redundancy, safety considerations, and first-hand equipment knowledge. The prediction narrows attention. The human adds context. Blind automation becomes risky when the cost of a wrong prediction is high. A false positive may trigger unnecessary work. A false negative may miss an important event. And some decisions carry financial, safety, compliance, legal, or customer consequences. This is where confidence thresholds, review queues, escalation rules, and approval requirements become architecture decisions. Human in the loop does not mean the AI failed. It means the system was intentionally designed around the risk and economics of the decision. Over time, some decisions may become more automated as confidence increases and the organization gathers evidence. Others may remain human decisions permanently. The goal is not maximum automation. The goal is better outcomes. Use prediction to help experienced people see important situations earlier, prioritize attention better, and make decisions with more information. That is often one of the lowest risk ways to move predictive AI from prototype into real operations. The demo usually proves that the prediction is possible. Production proves whether the organization can depend on it, and that requires much more than model accuracy. Start with logging. The system should record when predictions occur, what model version was used, relevant execution details, errors, warnings, and enough context to investigate unexpected results. Exceptions need predictable handling. External services fail, databases time out, files arrive late, records contain invalid values, networks disappear. A production application needs retries where retries are safe, and clear failures where they are not. Security and identity matter because predictive systems often use valuable enterprise data. Who can request predictions? Who can see them? Who can retrain or replace the model? Who can change thresholds? Who can approve a new version for production? Testing also expands beyond the model. You need tests around data preparation, feature calculations, business rules, integration points, API contracts, database rights, scheduled processes, fallback behavior, and deployment. If a new model version performs badly, can the organization roll back? If the feature pipeline changes, is it versioned with the model? Can you reproduce how a historical prediction was generated? That is model lineage. Auditability becomes especially important when predictions influence meaningful decisions. The organization may eventually need to answer, which model made this prediction? What data was used? When was it generated? What application version was running? Who reviewed it? What action was taken? Those questions become difficult if observability and lineage were never designed into the system. Cost tracking matters too. A predictive application may use cloud compute, storage, model endpoints, databases, queues, monitoring services, and external data. Someone should know what the capability costs to operate and whether those costs scale reasonably with business value. Then there is deployment discipline. Development, testing, staging, production, version control, automated builds, security scanning, change control, rollback, monitoring. None of these concepts are unique to AI. And that is exactly the point. Predictive AI does not get a waiver from professional software engineering. The model may be new technology. The production responsibilities are not. If the prediction matters to the business, engineer the surrounding system like it matters. That is the difference between a model that impresses people during a demonstration and a production capability the organization can actually trust, operate, support, and improve. Production predictive AI is not a model with a user interface wrapped around it. It is an engineered business capability that connects data, prediction, business rules, workflow, monitoring, human judgment, and operational controls. The organizations that design all of those pieces together will get far more value from predictive AI. You can explore more practical enterprise AI resources at ain.net.com. Thanks for watching.